Hello. In our last application of eigenvalues and eigenvectors, we'll be looking at the Fibonacci sequence. Now, I'm sure you've heard of Fibonacci numbers before, but just in case, let's go back to the situation in which this famous sequence first arose. First done as a mathematical puzzle by Fibonacci in the year 1202, so that is 818 years ago. He posed a problem in which in the first month there is one pair of rabbits, one young pair. In the second month, the same pair is still there. Now they're adults. And in the third month, there are two pairs because the black pair has now given birth to one new pair. So I have one pair, two pairs. In the fourth month, the black and the red pair are still alive, and the black pair have given birth to another pair, the blue pair. In the fifth month, the three pairs that were alive in the previous month are still here, but both the black and the red have now given birth to a new pair. So the rule for taking the population of rabbits from one month to the next is at the next month you have the number of pairs alive at the previous month still alive, plus some new ones. How many new ones are there? That's equal to the number of pairs of rabbits at the previous month. So the number of rabbits at time n plus 1 is equal to the number of pairs at time n plus the number of pairs at time n minus 1. And that is the rule for generating the Fibonacci sequence. In fact, here is Fibonacci's book from the year 1202. It's written in Latin. It was handwritten because this was before machine printing had been invented. He wrote this book to popularize Arabic numerals. He had been living with his family in North Africa, and he met people who were using Arab numerals, and in Europe at that time they were only using Roman numerals, which of course are much more difficult to do calculations with. Here are you can see the examples in red of the Arab numerals. They're not exactly the same as we would do today. 1, 2, 3, 5, 8, 13, 21. He promoted all of the algorithms for addition, fractions, multiplication that we know today. Well, that's a little bit hard to read, so let's have a look at it written out in modern text. Here it is. Well, there's still a problem. It's in Latin, but at least we can read the numbers now. And here we see the Fibonacci sequence coming up. 2, 3, 5, 8, 13. 5 plus 8 is 13. 8 plus 13 is 21. 21 plus 13 is 34. And he works it all out by hand up to 377, and then he says you can keep going in this way as many as you like. Here we are again. This work from 1202 translated into English. It wasn't translated until 2002 for the 800th anniversary. How many pairs of rabbits are created by one pair in 1 year? A certain man had one pair of rabbits together in a certain enclosed place, and one wishes to know how many blah blah blah. On it goes. And thus you can in order find it for an unending number of months. Still quite complicated, and he hasn't completely solved the problem because he hasn't worked out how many pairs of rabbits there will be after any number of months except for computing all the terms of the sequence. I think you can see that modern mathematical notation with variables and formulas and so on is much easier than what he's doing here, explaining everything in a very long-winded way in words. Just to sum up, what we want is a way to find a formula for the terms in the Fibonacci sequence 1, 1, 2, 3, 5, 8, 5 plus 8 is 13, 8 plus 13 is 21, and so on. And also, we want to understand how rapidly is that sequence growing as the number of terms increases. Okay. Let's try a more modern and more mathematical approach to finding a formula for the nth Fibonacci number. I will let Fn be the nth Fibonacci number. So F1 is 1, F2 is 1, and the rule for generating the next one is to add the two previous numbers. So Fn plus 1 equals Fn plus Fn minus 1. This is called a recurrence relation. I'm applying the same rule over and over again to generate the sequence. So 1 plus 1 is 2, 1 plus 2 is 3, 2 plus 3 is 5. The sequence will go 1, 1, 2, 3, 5, 8, 13, 21, and so on. Now, you won't be too surprised to hear that we're going to solve this problem using matrices, and in fact with eigenvalues. I don't see a matrix here. I'm going to introduce a matrix now, and you'll see in a while why I do it this way. So I'll let a vector xn, this will be a vector in R2. Vector xn will have two components, fn plus 1 and fn. N is going to go 0, 1, 2, 3, and the starting value x0 is going to be f1, f0. F1 will be 1. F0, I don't have a value. I'll just put 0 in there, and that won't upset the rule, because then f2 will be f1 plus f0. That's 1 plus 0. That's 1. So that's the starting rule. I'm going to rewrite my recurrence relation in terms of x instead of in terms of f. So xn plus 1, well, that's fn plus 2, fn plus 1. Fn plus 2, I'll get that from the Fibonacci rule. That's fn plus 1 plus fn. Fn plus 1, I'll just leave that as fn plus 1. Now that looks like a linear transformation of fn and fn plus 1. Let's write it as a matrix times a vector. So fn plus 1 plus fn, I write 1, 1. Fn plus 1, I just write 1, 0. You can check that that matrix times that vector gives me what I want. So it's the matrix 1, 1, 1, 0 times xn. So my recurrence relation written in terms of x is xn plus 1 is a matrix A times xn, where the matrix A is 1, 1, 1, 0. Now I've got a matrix formulation, I can get going. So x1 is A x0. x2 is A times x1, but x1 was A times x0, so I get x2 is A squared x0. x3 will be A cubed x0, x4 will be A to the 4th x0, and so on. So now I get a rule for xn. It's A to the power of n x0. There you see the 2 by 2 matrix A raised to the power n, and if you think back a few lessons, we worked out how to evaluate matrix powers. We did that by diagonalizing A using the eigenvalues and eigenvectors. So I have to take that 2 by 2 matrix A, 1, 1, 1, 0, and diagonalize it. That means I have to find the eigenvalues and eigenvectors. So the characteristic polynomial, that's the determinant of A minus lambda I. That's 1 minus lambda times minus lambda minus 1. It's lambda squared minus lambda minus 1. Doesn't seem to have any integer factors, so I use the quadratic formula, and I get the roots are 1 plus or minus root 5 over 2. Now the biggest root, that's going to be the most important one, 1 plus root 5 over 2, that's 1.618 dot dot dot, it's an irrational number. That's a famous irrational number that is called the golden ratio, and its symbol is phi, so I'm going to let phi equal 1 plus root 5 over 2 be the golden ratio. Then the second root, 1 minus root 5 over 2, the second eigenvalue, is 0.618. That turns out to be 1 over phi, 1 over the golden ratio. So my two eigenvalues are phi, the golden ratio, and 1 over phi. Now I need to find the eigenvectors. I'll let you do that as an exercise, that's not too hard. The eigenvector that goes with phi is phi 1. The eigenvector that goes with phi inverse is minus phi inverse 1. Using the eigenvalues and eigenvectors, I can diagonalize the matrix. Then I can find a formula for xn. So here we go. Xn is A to the power of n, x naught. That's A to the power of n times 1, 0. But A is equal to P d P inverse. P d P inverse, all to the power n, is P times d to the n P inverse. Now I just write down my matrix P, which has the eigenvectors of A as its columns, phi 1 and minus phi inverse 1. Then I write d to the n, where d is the diagonal matrix containing the eigenvalues. The eigenvalues were phi and 1 over phi. So d to the n is phi to the n, 0, 0, phi to the minus n. Then I need to write down P inverse. Well, my first matrix there is the matrix P. I need to work out its determinant. That comes out to be the square root of 5. Remember the formula for the inverse of a 2 by 2. The inverse of P is 1 over root 5 times 1 phi inverse minus 1 phi times the vector x naught, which was 1, 0. So I've got 4 matrices to multiply, and it's easiest to do the last multiplication first because of that 0 there. That will simplify things. Then I remember that I only need the last component, because that's fn. That comes out to be fn equals 1 over root 5 times phi to the n minus phi to the minus n. This is an exact formula for the nth Fibonacci numbers, and we found it using eigenvalues and eigenvectors, and in particular by diagonalizing the matrix of the linear transformation. So there's several curious things here. One is that we know that fn is an integer, because I get it by adding up integers, but the formula for fn involves irrational numbers, an irrational number raised to the power n minus another irrational number raised to the power n. Now phi inverse is 0.618, so this second term is getting smaller and smaller. The dominant growth here is given by phi to the n. So I also get a measure of the rate of growth of the Fibonacci sequence. The nth term is growing like 1.618 to the n, still exponentially fast, but slower than 2 to the n, for example. Plug in n equals 10. You do, in fact, get an integer. You get the 10th Fibonacci number is 55. They grow very rapidly. If 100 plug into that formula, you get 3.5 times 10 to the 20. It's a very large number. I don't know how far Fibonacci took it, but he didn't get up to F100. Now, this is not just a cute example of a math puzzle that someone thought up 800 years ago. What's going on here is iterating a linear transformation. So taking a simple rule to get from one step to the next by a linear transformation, and doing that rule over and over and over again, and looking what happens. That's a very, very simple system that applies to all manner of different situations, and it's very like what happens in physics, where the laws of physics give you a rule from going from one time to the next. Apply the rule again, you go to the next time. Apply the rule again, you go to the next time. And it's the cumulative effect of applying those same transformations from the current state to the next state, to the next state, to the next state, that produces all of the dynamical phenomena that are going on in the universe. There is, of course, one simplification here. This is a linear transformation. Some of the laws of physics are linear and some of them are non-linear. But even linear transformations, if you do them again and again, can produce very complicated phenomena if the vector x is high dimensional. To take one extreme example, in quantum mechanics, the transformation that takes you from one quantum state to the next, for example, in a chemical reaction or when an atom is moving around, that is in fact a linear transformation. And all the things that atoms and molecules do are just the effect of linear transformations done over and over again, producing complicated results. So there's much more going on here than just a bunch of rabbits.